I'm Professor Rad, and this is Precalc video 1-7, asymptotes. In this video, we're going to be looking at a graph and identify asymptotes from the graph. So we're not going to do any algebraic finding of asymptotes right now at this point in the semester. We're just sort of introducing the concept. And then as we delve deeper into particular functions throughout the semester, so like when we get to rational functions, exponential, logarithmic, trigonometric, and so on, we'll talk about how to find those specific asymptotes at that time. But for right now, let's talk about what an asymptote is and how to identify it from a graph. So if you would like to pause and copy down this definition of an asymptote, you may do that here while I'm out of the way. But an asymptote of a function is a line or other function that our function is going to approach. Now, you may have heard before that a function never crosses its asymptote. That is a lie. Functions can cross asymptotes. They are really just, they're describing the behavior of the function in two particular instances, either as the function gets closer to a particular point, or as the function goes off towards infinity on either end. So we're going to look at three different types of asymptotes in this example that I've drawn behind me. And for our purposes in this class, our asymptotes are primarily going to be linear functions. You could have quadratic asymptotes or wackier asymptotes if you wanted to, but for our purposes in this class, they're all going to stay linear. We're going to stick to linear asymptotes. So if you would like to take a moment and copy down the function f of x, you may do so. It goes through, it's got two pieces, these purpley pieces. It goes through the point -1, -1, and it goes through the point about 1 3/4, -1. So those are like my anchor points when I drew the graph. And the three dotted lines, we've got one here at -3, and we have another dotted line here at 1. And then we have another dotted line that goes through the point 0, -6, and it goes through the point 6, 6. So if you wanted to connect those two dots, you could get that dotted line there. And you can see that our purple function, when it goes to the left, kind of does this little doodly up and down nonsense, and then kind of swoops down here. And then this one sort of looks like a U, where it gets close to that vertical line. And then here it gets close to that slanted line that we drew. So it's kind of a real brief description of this function, I guess. But these red dotted lines are the asymptotes, and we want to talk about those. Let's talk about this one first, this vertical line here. So we're going to talk first about a vertical asymptote. So in this case, if I look at what's going on with my function, as I approach, I guess when x is 1, right? As I approach 1 from the right-hand side, this function gets close to that red dotted line, but it does not cross it. It just gets really close to it. And it approximates a vertical line the closer I get to when x is 1. And similarly, this one also gets close to a vertical line as x approaches 1. Okay. So basically, this function doesn't exist when x is 1. That would be a gap in its domain. So our vertical asymptote is when x equals 1. So if I were to ask you for the equation of the vertical asymptote, this would be the equation. Now there are two, I guess, additional notations we can use to describe the behavior of this graph. So I could say something like f of x gets close to positive infinity as x gets close to 1 plus. And I could say f of x gets close to negative infinity as x gets close to 1 minus. Now, as I was writing the notation, I was kind of writing, saying kind of what I was writing. It's not how I would pronounce this. So the way that I would pronounce this line here is f of x goes towards infinity as x approaches 1 from the right. So this little plus means that we are approaching 1 from the right. So as I approach 1 from the right-hand side here, the function is going up towards positive infinity. The second one says that f of x goes towards negative infinity as x approaches 1 now from the left. So that -1 means from the left. So as my x value gets closer to 1 from the left-hand side, the function goes down and goes towards negative infinity. These concepts are actually going to be super important in calculus. You're going to frame these concepts as something called a limit in calculus. We're not going to talk about limits in this class in any bigger sense than this definition here, this concept. So as my x value gets close to 1, my function either gets close to positive infinity because it's going up here, or negative infinity because it's going down here. So that's our vertical asymptote for this function. Let's talk about its horizontal asymptote. Now this function has one horizontal asymptote, and it's this red horizontal line here. And it's a horizontal asymptote because if we follow what this function does towards the left, we can see that this purple line starts out, the lumps kind of start out big, and then they get smaller and smaller and smaller. So think about, maybe somebody's signature or something going like this, right? And as it goes off towards the end, it looks more and more and more like a horizontal line. So that's what's going on with this function here. As we go off, as the x values go off towards negative infinity, the y value of this function is getting closer and closer to -3. So we have a horizontal asymptote of y equals -3. So again, if I were to ask you for the equation of this asymptote, this would be the equation of the asymptote. And if I were to write it out kind of as f of x goes towards blah, 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 like we did in the last example, I would say that f of x goes towards -3 as x approaches negative infinity. In other words, the bigger negative number I have for x, the closer and closer this purple squiggle is going to be to a horizontal, to a horizontal line. And if we look at what's going on the right-hand behavior for this function, we'll notice that this dotted line just kind of empty over here. There's no purple near this horizontal line. Okay. So we only have a horizontal asymptote for this function on the left-hand side. On the right-hand side, it looks like this purple line is getting closer to this diagonal red dotted line. So when you have an asymptote like that, we're going to call that an oblique asymptote. So when you have an oblique asymptote, in this case, it's going to be this diagonal line. And if I wanted to find its definition, which I do, I can find its y-intercept is at -6, and the slope looks like it's 2. Right? So if I go up 2 over 1, up 2 over 1, and so on, that's looking like how I graphed that red line. So my oblique asymptote is y has a slope of 2 over 1, which is 2x, and the y-intercept is -6. If I wanted to describe the end behavior, I would say that f of x goes towards 2x minus 6 as x goes towards infinity. So for very large positive values of x, this function is almost indistinguishable from this line 2x minus 6. They look basically like the same thing. So our vertical asymptote was describing what happened to the function located around a particular value of x. So at a particular value of x, we could see what was happening to this function. It either went towards positive or negative infinity, so much so that it looks like a vertical line the closer we got to 1. Whereas horizontal and oblique asymptotes describe the extreme end behavior of your function. So here, as we go off towards the left, we look like a horizontal line. And as we go off towards the right, we look like this diagonal line. So that's going to wrap it up for this video on asymptotes. Again, we're going to go into much deeper detail in the future, finding asymptotes algebraically. But right now, this is kind of what they look like visually. So I hope this was a good brief introduction to asymptotes. Have a wonderful day, and I will see you in the next video. Bye.